Angular velocity and its linear counterpart. So we have studied the relationship between angular displacement and its regular counterpart, that is linear distance, which are related by a formula distance equals radius times angular displacement. In this video, we are going to build a relationship between angular velocity and its linear counterpart. If a tennis ball attached to a string displaces through an angle delta theta in radians in time interval delta t, then time rate of change of angular displacement will be angular velocity, that is omega. If this ball rotates quickly, it is said to have a greater angular velocity, and if it rotates slowly, then it has a smaller angular velocity. The higher the angular velocity, the greater its linear counterpart, and vice versa. Delta theta over delta t tells us how many radians per second does the ball rotates through. What if I ask you how many meters per second does the ball rotate through? You would be like, that would be velocity, the distance of arc length over the total time taken, right? But that's not the case. That would only be the magnitude of velocity, not its direction. Because remember, we chose to deal with distance, the arc length, rather than its displacement, as displacement was less intuitive and weird for many reasons. This is speed, which is distance over time, still represented by v, but not with an arrowhead, and it is a scalar quantity, while velocity is vector, which is related to displacement. So we know angular velocity is delta omega over delta t, which gives radian per second. Here, radius times omega equals radius times delta theta over delta t. This seems familiar, isn't it? It is the distance covered, remember? So r times or radius times omega equals distance over delta t. Distance over delta t is the distance covered along the boundary over time, which is its speed or magnitude of the velocity. Note that this speed gives change in distance over time. It is just the magnitude of velocity and does not give us any direction. It tells us how fast this ball is moving along the boundary of the circle. Greater velocity means it is moving fast and vice versa. There is one point to be noted, and that is if the tennis ball rotates with a constant angular velocity, the speed, this v without an arrowhead, would be constant too. But velocity wouldn't be constant because velocity takes into account not only the magnitude but also the direction. And even if the magnitude remains constant, that is the speed, direction is still changing. With constant speed, it has changing velocity due to the change in the direction. You might say that as the ball is rotating, it does have speed and some direction, as we can see it, moving in a specific direction. So what is that direction? Let's do an experiment to understand this. Take a stone, attach to a spring and whirl it around. As it is rotating, leave it and see what happens. Which direction does it move in? Repeat it many times and you will see that the stone always moves tangent to the circle, which proves that the direction of motion is always tangent to the circle. Similarly, the direction of motion of a tennis ball is always tangent to the circle as well. So equation becomes radius times omega, which is the magnitude of the velocity, and its direction is always tangent to the circle. This equation tells us about the correspondence between angular velocity and regular velocity, that is tangential velocity. Thank you for watching. Like and subscribe for more such short and crisp educational videos. And also find us on social media platforms at Smartitude Official.